Welcome to Bodhi Unified Flow. I'm Dr. Miramathu, your host, and here we simplify complexity and amplify performance. Today's explainer is a deep dive into the absolute best practices for the design and pre-construction phase of MEP and building services. We're going to unpack how adopting an integrated MEP design with early clash detection literally makes or breaks a project. We'll talk about designing HVAC systems that actually hit those strict energy benchmarks, like the ECBC, and how to seamlessly integrate a smart building management system. We're also going to map out electrical systems that are future-proofed for EV charging, solar PV, and energy storage. And finally, we'll cover designing advanced plumbing with hydraulic modeling and integrating critical fire protection systems right from the earliest conceptual stages. It's a packed agenda, so let's jump right in. Here is our roadmap for today. First, we'll establish MEP systems as the vital organs of a building. Second, we dive into BIM and early clash detection. Third is HVAC efficiency and smart BMS. Fourth, we tackle electrical decarbonization with EV and solar. Fifth, we explore advanced plumbing and fire safety. And we'll wrap up with Section 6, covering the financial returns and our references.
By the end of our time together, you're going to have a solid grasp on leveraging BIM and automated clash detection to save some serious capital. You'll know how to navigate those ECBC HVAC benchmarks alongside BMS integration, plan for electrical decarbonization with EV and solar, and model advanced hydraulic and life safety systems.
Section 1, MEP, the vital organs. Let's look at why these systems are the beating heart of modern architecture.
Think about this for a second. MEP systems now account for up to 60% of total construction costs in commercial buildings. 60%. With intensive tech integration, aggressive sustainability targets, and complex automation, these systems are absolutely not just an afterthought anymore. You can't just figure them out later in the build. They are the primary engine driving a building's economic and environmental viability. Getting this integrated flawlessly in the pre-construction phase really dictates the financial success of the asset's entire lifecycle. And here is exactly why that early pre-construction window is so critical. $4,200. That is the average cost to resolve just one single design clash once you are on site during construction. Imagine dozens or even hundreds of these clashes popping up. It's a massive, hidden margin killer. By weaving architectural intent seamlessly with complex MEP needs early on, we stop these cascading costs dead in their tracks. We're essentially moving the problem-solving from the very expensive physical world into the highly efficient digital world.
Moving on to Section 2, BIM and early clash detection. Let's examine the virtual brain and nervous system of our framework.
This virtual design workflow happens in 4 highly coordinated steps. First, model aggregation. This is where we create a single unified federated file pulling from all the different disciplines: architectural, structural, and MEP. Second, we run a preliminary quality check for data integrity. We have to ensure all those models are speaking the exact same digital language. Third, we deploy automated clash detection using complex, rules-based software to flag any overlaps. And finally, digital resolution. This allows the multidisciplinary teams to fix hard, soft, and workflow conflicts virtually. We get all of this sorted long before a single piece of copper is cut or a concrete core is drilled.
The financial impact here is just undeniable. If you look at the traditional, siloed method, projects typically bleed about 5 to 20% of their entire budget purely on construction rework. But when you shift that clash resolution into the digital design phase with a fully BIM integrated method, you reduce site rework costs by an astounding 30 to 50%. In fact, a landmark Stanford University study looking at 32 major commercial projects proved an 18% average total cost savings just by adopting this workflow. So BIM is definitely no longer an optional upgrade, it's mandatory financial armor.
Section 3, HVAC efficiency and smart BMS. It's time to talk about balancing performance in the lungs of our building.
To hit aggressive energy goals today, the Energy Conservation Building Code, or ECBC, offers a really structured, tiered framework. We start with the baseline ECBC tier, targeting a solid 25% energy reduction using minimum BE star labeling. If you step up to ECBC Plus, you're looking at a 35% reduction, which requires 3-star rated chillers and an improved building envelope. Or you can push the limits and aim for Super ECBC. That drives up to a massive 50% energy reduction by mandating premium 5-star rated chillers and deeply integrated daylight harvesting techniques.
Now, pushing for efficiency is great, but we absolutely cannot compromise human comfort. Enter TSPR, or the Total System Performance Ratio.
Instead of just zooming in on the efficiency of an isolated fan or one specific pump, TSPR steps back and evaluates the whole system's thermodynamic dance. It measures how heating plants, cooling plants, air distribution, and energy recovery systems all interact holistically. This ensures that while we aggressively cut power consumption, we don't accidentally freeze or overheat the occupants and ruin our occupant satisfaction benchmarks.
Taking this holistic view prevents a massive, yet often ignored operational threat: energy drift. This is the invisible, gradual degradation of system performance over time. It's silent, but incredibly expensive. By insisting on an open building management system architecture, using universal communication protocols like BACnet or Modbus, we can plug in artificial intelligence and digital twins to catch these anomalies early. Imagine a scenario where a system is heating and cooling the exact same room simultaneously because of a sensor conflict. An open BMS catches that flaw during the design and commissioning phase, preventing years of wasted energy.
Section 4. Electrical, EV, and solar. Let's move to the powerhouse of the design phase, electrical modernization.
We're seeing a major regulatory shift right now that is actively rewriting our electrical load calculations. For instance, India's model building bylaws now mandate that 20% of vehicle parking in new constructions must be EV ready. If you don't calculate for this massive electrical draw early in pre-construction, your transformers are going to be drastically undersized. Your design absolutely must include smart charging protocols and dynamic load limiting. This prioritizes critical vehicles and ensures your building provides adequate charging without completely destabilizing the local grid.
And when it comes to integrating distributed energy resources like solar PV, engineers really have to rely on a strict, proactive 5-pillar design approach. First up is site evaluation. Second is topographical analysis to really understand shading and panel angles. Third is layout configuration. Fourth, accurate energy yield forecasting. And fifth, overall project evaluation. This isn't just about slapping some panels on a roof. It's a rigorous methodology for building resilient microgrids that slash peak demand charges and keep the lights on during grid outages.
Here is a critical pre-construction hurdle that catches a lot of folks off guard: the 120% rule, outlined in NEC 690.64. Basically, it dictates that the combined current from your main utility service panel and your solar inverter cannot exceed 120% of your electrical panel's busbar rating. If you ignore this, you risk dangerous overheating and potential electrical fires. Factoring this mathematical rule in early ensures your infrastructure can safely handle added solar capacity, saving you from having to rip out and replace entire electrical panels at the very end of construction.
Section 5. Advanced plumbing and fire. Securing hydraulic performance and critical life safety systems.
Modern plumbing is fully embracing what we call the circular water economy. By using advanced hydraulic modeling software like EPANET, engineers can seamlessly integrate decentralized recovery systems right from day one. We are talking about gray water recycling, reusing sink and shower water for flushing, and rainwater harvesting to capture raw stormwater. The impact? You can slash a building's potable water use by an incredible 45%. But here is the catch. These massive tanks and treatment systems need a huge spatial footprint. That means architects and public health engineers have to be totally aligned during the earliest concept phases.
Finally, fire protection. It's no longer just about laying out basic sprinklers. It's a highly complex, multidisciplinary interface. We have to rigorously program cross-system logic like elevator recall sequences. For example, if a primary smoke detector in an elevator lobby trips, the system instantly overrides the elevator, recalling it to a primary designated floor. But what if that primary floor has smoke too? Well, a secondary recall automatically sends it to an alternate safe floor. Programming this logic early guarantees safe occupant egress while instantly clearing the vertical path for firefighters.
Section 6. Summary, returns, and references. Let's look at the financial impact and review our strategic conclusions. Now, you might be thinking, integrated MEP design sounds great, but doesn't it add a lot of upfront cost? Yes, it does add some upfront modeling and coordination costs. However, long-term lifecycle analysis completely flips the script. The payback periods for deeply integrated ECBC-compliant designs are exceptionally fast. We are looking at an average return of just 6.7 years for hotels and about 8.9 years for incredibly complex high-draw assets like multi-specialty hospitals. After that payback period, those massive energy and water savings drop directly to your bottom line. So, we've successfully worked through our learning objectives today with this comprehensive 6-point framework. We covered mandatory BIM workflows,
whole building energy modeling for EBC compliance, future-ready electrical planning, decentralized water management, open BMS architecture, and integrated life safety interfaces. Remember, these aren't just engineering tasks. They are absolutely your strongest financial strategies to de-risk major infrastructure projects.
I want to leave you with a final thought to mull over. In the modern built environment, the cost of inaction during the design phase is simply too high. When rework costs thousands of dollars per single clash, and energy drift silently drains your operational budget year after year, hope is not a strategy. So ask yourself, are your building's vital organs economically optimized for the extreme complexities of the future? And how will you apply these integrated design practices to guarantee success on your next major project?
Here are the key standards, codes, and rigorous research papers that power today's insights, including the ECBC User Manual, CEA regulations, and that fantastic Stanford University BIM research. Thank you so much for joining me on this explainer at Bodhi Unified Flow. I'm Dr. Mary Muthu. Until next time, keep simplifying complexity and keep amplifying your performance.